Spheres can be stacked to form a tetrahedron by using triangular layers of spheres. Each sphere touches the 3 spheres below it. The diagrams show a tetrahedron with 4 layers and the layers of such a tetrahedron. An internal sphere in the tetrahedron is a sphere that touches exactly 3 spheres in the layer above. For example, there is one internal sphere in the 4th layer, but no internal spheres in the first 3 layers. A tetrahedron of spheres is formed with 13 layers, and each sphere has a number written on it. The top sphere has a 1 written on it, and each of the other spheres has a written on it the number equal to the sum of the numbers on the spheres in the layer above with which it is in contact. For the whole 13-layer tetrahedron, the sum of the numbers on all of the internal spheres is. What we will do is just concentrate on a few of these and then try to look for some sort of pattern. So the very first one, of course, will have the number 1 on it. Now these ones will also have 1s because they only touch the top sphere. Now the next layer, the numbers start to get a little bit different. If you just concentrate on what the question is telling you, that each of the other spheres has written on it the number equal to the sum of the numbers on the spheres in the layer above with which it is in contact, you can notice that the numbers would be 1, 1, 1, 2, 2, 2. Okay, take a minute, pause the video, try to figure out why that is true. And then the next layer, again, 1, 1, 1, because those only touch the corners. And then these guys, they touch the 2 and the 1, so they add up to 3. And then the internal sphere touches 3. It touches this guy, and this guy. So that sum will be 6. And the good news is that these 3 or 4 layers are enough to figure out the pattern. And the patterns are as follows. The first pattern that you probably have noticed, that all the corners will be equal to 1, no matter what. No matter how many layers we get, all of these corners, which are these guys right here, they will always be equal to 1. So that's the first pattern. The next is that the sum of the spheres in the outside edges have a very distinct pattern. They have a pattern of 1, 2, 4, 8, and so on. And what I mean by the outside spheres in the outside edge is these guys. This is an outside edge. This is an outside edge. And this is an outside edge. So you notice those sums, this one was 8, this one is 4, this one is 2, and so on. So we can create a little simple formula that the sum of the spheres in the outside edge for the kth layer is 2 to the power of k minus 1. The third and final pattern that will help us solve this question is the sum of all the spheres, if you add them all up in each layer, have a pattern 1, 3, 9, 27, and so on. So therefore, for the kth layer, the sum of all the spheres will be equal to 3 to the power of k minus 1. And that's it. So these 3 things will help us figure out the question, and in particular, the sum of the numbers on all of the internal spheres. Now, so far, there's only one internal sphere, this guy right here. But obviously, there's going to be many, many more. We will now use these patterns to figure out the sum of all the internal spheres. Remember, we only want internal spheres, so that will be my column over here. This one will be the number of the layer. Is it the first layer, second layer, and so on. This column will be the sum of all the spheres, and this is 3 to the power of k minus 1. Remember, the sum of all the spheres that are in that layer. This one is important. This is the sum of just the outside edges. Now, what's the formula for that? Well, let's go back and look at a simple example. And the good news about this question is that you don't need to look at anything other than these three. Let's just look at this one. If I want the sum of only the outside edges, all of them, this formula is good only for one outside edge. But what if I want all of them? I want this, this, and this. Well, I obviously can use that formula, but if I do, I have to multiply it by 3. So this 2k minus 1, obviously I have to multiply by 3 since there's 3 outside edges. But the problem with that is then I overcount the corners. The 3 corners, I count them twice. So then I have to subtract 3. So this formula gives me the sum of all the spheres in the outside edges. 2 to the k minus 1 multiplied by 3 and then subtract the 3 corners. So put that in here, 3 times 2 to the k minus 1, and then from that we subtract 3. And here we go. So we've got to do some math here. And I will just do a few. If k is 1, 3 to the k minus 1 is 1. If k is 2, 3 to the k minus 1 is 3. And then 9, then 27, and then 81, and so on. So I'll fill all these out. And in a very similar way, I've got to figure out these numbers. But the good news is that for the first few, there are no reason to figure out these numbers because there's no internal spheres. You remember, the first time an internal sphere appears is in layer 4, which is this layer right here. So the first 3 we don't need to calculate. But for the 4th layer, obviously we do. When k is 4, this formula right here, 3 times 2 to the k minus 1 minus 3 is 21. And then this is 45, and so on. I'll fill in all of those. Now, the sum of the internal spheres, obviously, will be you take the sum of all the spheres, and then you subtract from it the sum of the outside edges. And if you do that, you will get the sum of the internal spheres. So the first one is 6, and as you can see, it definitely matches that diagram. Now, we didn't have any other diagrams because it would be very complicated and obviously very time-consuming, but we don't need the diagrams. We can just use these numbers. So 81 minus 45 is 36. 243 minus 93 is 150, and so on. So I'll fill all of these. And now we are at the final step, which is adding them all up. So I've got to add all of these to get the total sum of all the internal spheres on all the layers. And when you add up that entire column, you get a final number of 772,626. 772,626 is choice E. 3 identical cones each have a radius of 50 and a height of 120. The cones are placed so that their circular bases are touching each other. A sphere is placed so that it rests in the space created by the 3 cones as shown. If the top of the sphere is level with the tops of the cones, then the radius of the sphere is closest to. This diagram illustrates the cones if you're looking at this from the perspective of just their bases, the circular part of the cone. And you'll notice, of course, that they touch each other. And what I'm going to draw is the centers of these circles, and then I'm going to connect them like that. And these circles are all identical, And therefore, the distance from the centers are also identical, because this is the radius, and so on, right? So this is an equilateral triangle, and that represents the center of this diagram. Now, one thing that's important to understand is that when you place this sphere in that position, the center of the sphere will line up exactly with the center of this equilateral triangle. And what is the center of an equilateral triangle? Well, it is known as a centroid. And now I'm going to draw the diagram to illustrate what is the centroid, and we then have to figure out the distance from the vertex to that centroid. So here is our equilateral triangle, and the first thing I'm going to do is draw lines from the vertex to the opposite sides, like that. And the centroid is this point right here, that one that I just drew the red dot. And we have to figure out the length of this segment from the vertex to the centroid. So how do we do that? Well, one thing we know that this is most likely a 30, 60, 90 triangle. This is, of course, a right angle. This whole angle was 60 because it's an equilateral triangle. So if I cut it in half, this angle is 30. And therefore, since this angle must be 90 minus 30, it's 60. So it is indeed a 30, 60, 90 triangle. And if I draw that triangle over here, I will be able to illustrate what the distance is from here to here. Well, we know that from here to here is the radius of the cone, and they told us in the question stem that that is equal to 50. So this is 50 in terms of a numerical value. But because we know that in a 30, 60, 90 triangle, the ratio of the sides are 1, 2, and root 3, we can now figure out this side. That side, if I call it x and use the ratios, x over 50 is equal to 2 over root 3. So therefore x is equal to 100 over root 3. So that represents the distance from the vertex of the triangle to the centroid, and that is going to help us later in the question. So now I have to bring in the sphere. So far we've just been discussing the three cones, but remember there's a sphere that has been placed, and now we have to try to figure out the radius of that sphere. So this diagram shows you how that sphere has been placed. Now I have to draw it in 2D and try to figure out the radius of that sphere. So here is my 2D representation. This is the cone, this is the sphere. I'll call this point A. I'll call this point B right here. And then we'll call this, of course, the radius, big R. This is also a radius of the sphere, big R. And this point that is tangent, I'll just call that C. And then top to bottom, this green line represents the height, which is the same as the height of the cone. And if you remember, that height is equal to 120. They give you that in the question stem. All right, now this from there to there represents the radius of the cone. And if you remember, that was 50. Now we come to the point of the question where this value comes in. Remember, 100 over root 3 was the distance from the vertex to the centroid, right here. The distance from the vertex to the centroid. And if you remember, the sphere will align with the centroid, the center of that sphere, will align perfectly with the centroid. And therefore, since this is the sphere, this is the centroid right there. And this is the center of this sphere. Those two will be aligned. They'll be right in the same line top to bottom. And this, of course, represents this point, the center of the cone, the circle part of the cone. So therefore, from here to here is essentially the distance from the vertex of that triangle to the centroid. Let me show you in this diagram. This is the center of that cone. This is also the vertex of that triangle. And if you draw a line from the vertex right here to the centroid right here, that represents this distance from here to here. And I think that is probably the most challenging part about this question. So that distance is 100 over root 3. Okay? Now 100 over root 3 is approximately 57.73. So therefore, this distance from here to here has got to be 57.73 minus 50. So this is approximately 7.73. The distance from there to there. Okay? Now, one important point that needs to be mentioned in this question before I move forward is that you've got two tangents. One is from A to C, right there. That C point is tangent to the circle. And the other one is from A to B. That point B is tangent to the circle. And because AB and AC are both tangent to the sphere, it's really the sphere that we are talking about, AB will be equal to AC. And that is something that we will need to use a little bit later in the question. So now we have to figure out R. So what I would like to do is draw a line from the center of the sphere down to this point right here. And the reason is that's going to help me figure out R. And I will label that distance Y. Okay? And then this is, of course, a tangent point, C, so that means that is a right angle. And this is a perpendicular that we had drawn earlier, so that is a right angle. So now, this will be two Pythagorean relationships. So the first one involves this triangle right here. And that will give me the following equation. Y squared is equal to 7.73 squared plus this distance. Well, that distance is the full top to bottom, which is h, minus this radius, minus r, like that, all squared. And that gives me y squared is equal to 59.83 plus h is 120, so it's 120 minus r, all squared. So that's the first equation. The next equation will come from this right triangle right here. And that one will give me y squared is equal to r squared plus this distance right here. And I can call this point D, and therefore we can just call that CD. But what's CD? It will help if I knew the numerical value for CD. That way I can just set these two equations equal to each other and solve for R, and we'll be done. So how do we figure out CD? That's the second last step to this question. Well, let's figure that out. First, we will need to figure out the distance from A to D, that whole distance. And that can be done using Pythagoras, once again, using this triangle. Using that triangle, we have h squared plus this small r squared is equal to AD squared. H, of course, was 120. Small r was 50. And then we have AD squared. Solving, we get AD is equal to 130. All right, so we've got part of that. Now we also know that AC is equal to AB. We figured that out earlier right here. So AD minus AC would give me the numerical value for CD, like that. AD we just figured out was 130. AC is the same as AB. And AB, we know, is from here to here, which is the same as here to here, which is 100 over root 3. So 130 minus AB, which is equal to 100 over root 3, which is 57.73, is equal to CD. So therefore, the numerical value for CD is approximately 72.26. And there we go. We can put that back into this equation, and we'll get y squared equals large r squared, which is the radius of the sphere, plus 72.26 squared. And now we can set this equal to that and solve for r. So 59.83 plus 120 minus r all squared is equal to r squared plus 72.26 all squared. And this will help us solve for the radius of the sphere. So here we go. This becomes 59.83 plus 14400 minus 240r plus r squared is equal to r squared plus 5222.2. The r squareds cancel, and I'm going to put the 240r on this side. And all of these numbers, when combined, give you a value of 9237.63 approximately. And solving for r, you will get a value of 38.49. And this is the numerical value of the radius of the sphere, 38.49. Let's go back and see what are the answer choices. 38.49 is closest to answer D for number 25. A cylinder has radius 12 and height 30. The top circular face of the cylinder is the base of a cone, and the center of the bottom circular base of the cylinder is the vertex of the cone. A sphere is placed inside so that it touches the cone, the base of the cylinder, and the side of the cylinder as shown. Which of the following is closest to the radius of the sphere? Let's do some labeling. First, let's draw the radius of that sphere so that it touches the bottom right there. And then the same to touch the side and to touch the tangent point of the cone. And at this point, we have to draw some lines that will help us. The first is from this corner right here to the center of the sphere, and the next one is from the center of the sphere to the vertex of that cone. And now there's a very important property that we must talk about. This line right here is a line that originates from here and goes all the way to the tangent point. This line is the same. It originates from that red dot to the tangent point. And there's a rule that when you have such a situation, those two will be equal. And that's going to be very important. So let's do some labeling now, just concentrating on that. From here to here is the radius of that cylinder, and that they've told me is 12. From there to there is the same as there to there, which is the radius of the sphere. So I'll just call that r, this distance right here. And therefore this distance from there to there must be 12 minus r, from here to here. And as we have established, this distance is the same as that distance, so that is also 12 minus r. 12 minus r. Okay, and we are going to do something very similar, that when you have this point and you draw a line to the sphere, tangent to it, and then you have the same point emanating another line that hits the sphere at a tangent point, those two lines will be equal. So this distance is the same as that distance. Now, this distance right here is 30 minus r, since the top to bottom height is 30 and this is r, same as that. And therefore, this distance must be 30 minus r. So there we go, 30 minus r. So that pretty much completes the labeling of the diagram, and that's pretty much all there is to it. Now all we have to do is just use Pythagoras, Pythagorean theorem, on this big triangle right here, since it's a right triangle. So that means 30 minus r, or actually the full height, not 30 minus r, 30 top to bottom squared, plus this, which is 12 squared, is equal to the hypotenuse, which is 30 minus r plus 12 minus r, all squared. So this is 900, this is 144, this is 42 minus 2r, all squared. This is 1044, 42 minus 2r, all squared. And then you don't need to expand it, just take the square root of both sides. It'll be a lot quicker. 32.31 approximately is 42 minus 2r. And therefore 2r would be 42 minus 32 minus 31. And when you do that math, you get r is equal to 4.84 approximately. And therefore, number 22, the answer is A. A container in the shape of a triangular prism stands on one of its triangular faces. 3 spheres of radius 1 are placed inside the container, each touching the triangular bottom. Each sphere touches 2 of the rectangular faces of the container, and each sphere touches the other 2 spheres. A 4th sphere of radius 1 is placed on top of the 3 spheres, touching each of the 3 spheres on the top of the prism. The volume of the prism is closest to. This question is going to be done in a few steps. Step number 1 is the volume formula. And that volume formula is just going to be the area of the base, which is a triangle, 1/2 base times height, times the height of the entire prism, and I'll just call that large H. So there we go. That is the volume. So individually, I obviously have to figure out the value of B, H, and large H. So the first thing I want to do is draw the base, which is an equilateral triangle. That's the only way it could be. And let's see what happens when I put in 3 spheres. Now, the challenge here, of course, is that we are dealing with a question that talks in 3D, but my diagrams will be in 2D, but eventually I'll give you a 3D diagram. But for step number 2, a 2D diagram will be sufficient. So let's draw in those 3 circles that will represent our spheres. So here is the base, and each of these red circles represents a sphere. So what I'm going to do, the first thing, is draw the radii. And those radii will help us sort of get an understanding of what is the sizes of the lengths. So here's the first one, that's tangent, right? And then from the center of the circle, we draw another one. Let's connect these. And that should be good enough to figure out the lengths of this triangle. Because remember, that's going to be this part right here. I have to figure out the base and the height. Okay, so each of these spheres has a radius of 1. So this is 1 right here, the distance from there to there. And this is 1 from here to here. Similarly, this is 1, and this is 1. So this is 1, this is 1, this is 1, this is 1. Okay, now concentrate on this triangle right here. That is a 30, 60, 90 triangle. How do I know? Well, one thing is for sure, the way I drew this is a tangent, so that's a right angle. And then because it's an equilateral triangle, that angle there would be 60. So if you chop it in half, this little guy in here will be 30 degrees. And therefore this angle right there, this angle from here to here, that would be 60. And you guys, if you're in grade 10 and you're at this point of the math contest and you're practicing these kinds of questions, this should be pretty self-explanatory. So that 30, 60, 90 triangle, I'll just draw a rough sketch of it like that. This is 30, 60, 90. And then we know that this side is equal to 1. So I want, what is this side? Because that's going to help me figure out the length of that side. Well, according to 30, 60, 90 triangles, the ratio of the sides, x over 1, will be the same as root 3 over 1. So x is just root 3. So there we go. So this distance from there to there is root 3. And then because of the symmetry of the diagram, that will also be root 3 over there. So this entire base looks to me like it's root 3 plus 1 plus 1 plus root 3, which would be 2 plus 2 root 3. Okay, so might as well plug that in there. Why not? 2 plus 2 root 3. Okay, so next I'll concentrate on h, and then at the end we will figure out our value of the big H. Okay, well h, small h at least, is right there. I can figure that out pretty easily. Again, using a 30, 60, 90 triangle. So that 30, 60, 90 triangle this time is this guy. So let's just draw a very brief sketch of that. This is my h, and this is 90 degrees. This angle of 60, and therefore this angle is 30. So this h and this side, which is 1 plus root 3, will help me figure out the value of h. So again, using the angles of a 30, 60, 90 triangle, the ratio of the sides are always 1, 2, and root 3. So h over 1 plus root 3 is equivalent to root 3 over 1. So h looks like root 3 plus 3. Okay, put that in here. Root 3 plus 3. All I have to do now is figure out h, the big H, and I'm done with the question. So what is big H? It's the height of the entire prism, so top to bottom. And now I need to put in a 3D diagram to sort of explain that. So here we go. So here is a 3D diagram of one sphere sitting on top of 3 spheres. And we want to figure out height, top to bottom, all the way from the top to the bottom like that. That would be this height right here. So how do we do that? We're going to break it up into 3 segments. The first segment is from here to here. The next segment is from the center of one of the bottom spheres to the very bottom. And the third is from here to the base of that triangle. You notice there's this triangle here. That is where that third distance will stop. Okay, a couple of these are very easy. From here to here, that's just the radius of the sphere, so that's just 1. From here to here, that's also the radius of the sphere, so that's 1. So now my challenge is to find this, and that is not as obvious. Well, it's not going to be that difficult. I need to label it first, so I'll just call it small h. I don't want to make any unnecessary terminology. And then remember, at the end, h, the big H, is got to be the whole top to bottom. So don't think that it's h. It's going to be h plus 2. H plus this one plus this one. Okay, so now let's talk about how do I figure out that h. Let's put, there you go, that h. Well, we are going to use Pythagoras. And Pythagoras, or Pythagorean theorem, on this triangle right here. So it's going to be this plus this and that. Those three sides will be the triangle that help us figure out h. And this being a right angle. So let's see what we can label first. This is of course h, and we don't know what it is. From here to here joins the centers of two spheres, so it's just going to be 2 times the radii. So that's just going to be 2. That's easy. Now comes the task of finding this side right here. That is challenging, but we'll be able to do it. I'll just call it x for now. Once I find x, I can easily find h using the Pythagorean theorem. So here we go. Now what I've done next to help figure out the value of x is drawn a triangle. Now that triangle that I just drew is this triangle right here. That one. I just drew it sort of flat, like a bird's eye view. And now let's talk about what is h and x. Well, h obviously is in 3D, so I'm not going to worry about that right now. I'm just going to concentrate on x right here. Well, the first thing we need to draw are these lines that are perpendicular bisectors, basically. Once you draw that, it'll be obvious what x is. X will be the distance from here to here, because this point that the h touches is the centroid of that triangle, and this is the centroid right there. So you're going from a vertice to the centroid, so that's obviously from here to here. That is x. Okay, how do I figure out x? Well, what are the dimensions here? From here to here, which is the side of that equilateral triangle, is a distance between 2 centers of the spheres. So that distance is going to be 2 times the radii. The radii is 1, so 2 times the radii is 2. So this is 1, this is 1. And therefore, since this is a right angle, this is 60. Therefore, if you chop it in half, there's is 30, and this is 60. Once again, we've got a 30, 60, 90 triangle. And therefore, x over 1 is the equivalent of 2 over root 3. So if we rationalize the denominator top and bottom by root 3, you get 2 root 3 over 3. And there you go. We are almost done. Now that we have x, I can use this triangle to figure out h using Pythagoras. So x squared plus h squared is equal to 2 squared. So we got 2 root 3 over 3 all squared plus h squared is 4. H squared would be, what's that? 4 times 3 over 9. So that's 12 over 9. So 4 minus 12 over 9. And that's going to be 36 minus 12, so 24 over 9. And therefore h is equal to, I think I can reduce this, divide top and bottom by 3, 8 over 3. So h is root 8 over root 3. Okay. Now remember, big H is h plus 2. Don't forget that. So this is going to be root 8 over root 3 plus 2. All right, we're done. Well, almost. So remember this formula. All I had to do was figure out h, or big H, and I just did. It's root 8 over root 3 plus 2. Okay, now all I have to do is crunch out those numbers. So get out your calculator. and see what you get for these numbers. And when I do, I get, well, obviously 0.5 for that half. This 2 plus 2 root 3 is approximately 5.4641. Then we're going to multiply by root 3 plus 3. So that's 4.732. And then finally this guy, root 8 over root 3 plus 2. That is approximately 3.633. And when you crunch out all those numbers, you get approximately 46.97. And therefore, the volume of the prism is closest to, 46.97 is closest to 47 among the answer choices, which is E for number 23. Mike has two containers. One container is a rectangular prism with width 2, length 4, and height 10. The other is a right cylinder with radius 1 and height 10. Both containers sit on a flat surface. Water has been poured into the two containers so that the height of the water in both containers is the same. If the combined volume of the water in the two containers is 80 centimeters cubed, then the height of the water in each container is closest to. Well, the height, they're saying, is the same. So if this is h from here to here, then this is also h from here to here. Okay. Now they're saying that the combined volume of the two containers is 80. So 80 is equal to the volume here and the volume there. So the volume in the first one is going to be length times width. So that's 2 times 4 times the height. The volume here is a little bit different. It's pi r squared times the height, like that. So this becomes 80 is equal to 8h plus pi r squared. Well, r is 1. That's given in the question, so this becomes 1 squared. So this now becomes 80 is equal to 8h plus pi h. Factor out the h and you get 8 plus pi is equal to 80. Isolate for h and you get 80 over 8 plus pi is equal to h. Get out your calculator. Pi is approximately 3.14, so if you add 8 to it, it becomes 11.14. And now you get out your calculator, and 80 divided by 11.14 is approximately 7.18. And therefore, the one that is closest in the answers is this guy right here, 7.2. So number 23, the answer is B. A cone is filled with water. Two solid spheres are placed in the cone as shown in the diagram, and water spills out. The spheres are touching each other. Each sphere touches the cone all of the way around, and the top of the top sphere is level with the top of the cone. The larger sphere has a radius twice that of the smaller sphere. If the volume of the water remaining in the cone is 2016 pi, what is the radius of the smaller sphere? The volume of a sphere with radius r is 4/3 pi r cubed. The volume of a cone with radius r and height h is 1/3 pi r squared h. We must label this diagram, and here we go. I will label it A, B, C, and then we'll call the center O, we'll call this center Q, and the very bottom we'll call P. Now, this from here to here, AC, represents the radius of the cone, so I'll just write RC there. This is the radius of that small sphere, we'll just call it R, obviously, and these guys are the radius of, or the radii, I should say, of the large sphere, and they told me that the large sphere, the radius is twice of the smaller sphere, so I can just write 2r right here and 2r. And these are 90 degrees, just in case you cannot see that. That's 90 and that's 90. Why? Because those are tangent lines. They touch the other line And if it's tangent, it will create a 90-degree angle. And this is also a radii, so that's also 2r. And I think that's pretty decent labeling for now. So let's move ahead with the question. The first step in this question is to understand that we have a similar triangles relationship. And those similar triangles are triangle OTP being similar to triangle QUP. So OTP, this is T and this is U. So OTP is this triangle right here, and that's similar to QUP, and I hope you can see that. They're pretty much got the exact same angles. So based on that, OT over QU is the same as OP over QP. Well, OT is 2R and QU is R, and that's the same as OP over QP. So that basically means when the R's cancel out that 2QP is equal to OP. All right, so that is very helpful, and that allows us to get a relationship between the height, which is the top to bottom, that's the height, H, of the cone, to R, and that's pretty much going to be what we need to solve this. All right, well, OP, which is the distance basically from here all the way down to there, is equal to OQ from here to here plus QP from there to there. So OQ plus QP. And OQ from here to here is 3R. It's this guy plus this guy. So that's 3R right there. So put that in here, 3R. And then QP, well, QP I don't know yet. So I'll just leave it there for now. But I know this relationship, that 2QP is equal to OP. So that's very helpful. So instead of this OP, I'll just put in 2QP. So there we go. 2QP is equal to 3R plus QP. And then if you put 1 QP on the other side, we get just QP is equal to 3R. So there we go. That's a very helpful finding, that the distance from Q to P is 3R. So I'll just put that in here, 3R. And then also we know that 2QP is equal to OP. So that means 2 times QP is equal to 6R, and that's equal to OP. So that is OP. So those are two very important findings. Now what's H, the height of the cone? Well, the height of the cone is all the way from C down to P. Okay, let's count now. 2R, 2R, that's 4, 5, plus 3, 8. So the height is 8R. So those are very, very important findings. And now we can proceed with the second part of the question. The second part involves getting the radius of the cone in some sort of a relationship with R, something. So that is what we have to do. Because here we got the height in terms of R. So we have to now get the radius of the cone in terms of R. And once we have those two things, we can solve the question. Well, to do that, we have to use another similar triangles relationship. This time the triangles are ACP and OTP, a triangle that we had already looked at. So let's look at that now. Where is ACP here? ACP, so all of that big guy right there, that's one triangle. And then OTP is this one, OTP. Those are similar triangles because they share the same angles. So that basically means that AC over OT is equal to CP over TP is equal to AP over OP. All right, so let's label in AC is RC, the radius of the cone. OT, do I know anything about? Yeah, it's 2R. Okay, great. CP, that's the height, remember? And the height, I already figured out a relationship, so that's 8r. TP, do I have anything? TP, I don't really have anything yet. Okay, so I'll just leave TP for now. AP, again, I don't think I have anything for AP just quite yet. So I'll just put in AP for now. And then OP, yeah, that one I have. From O down to P, that's going to be 2 plus 1 plus 3, and that's 6R. Okay, so that's a pretty good set of findings. However, I'm going to need to know the value of TP in order to really figure this out. And that's not a problem because I can use Pythagoras. I can use Pythagoras on that triangle right there to figure out TP. So TP squared plus TO squared is equal to OP squared. So that means TP squared plus TO, what is that, 2R squared is equal to OP squared, and OP was what, 6R, right? So there we go. So that means TP squared is 36R squared minus 4R squared. So that's 32R squared is TP squared. So TP is going to be root 32. So what's that, 4 root 2? 4 root 2R. Okay, great. So now we can go back and use that relationship. So RC over 2R is equal to 8R over TP, which is 4 root 2R. Okay, so that means RC is equal to 16 over 4 root 2R. And that, of course, that simplifies to 4 over root 2R. All right, great. Exactly what I needed. RC in terms of R. So now that we have this relationship and we have this relationship, we can now solve the question. So here we go. If you were to interpret the question correctly, you would write the following: that the volume of the first sphere and adding to that the volume of the second sphere plus the volume of water, which they had said is 216 pi, equals the volume of the cone, right? Because you have the volume of the first big sphere, the volume of the second sphere, and all the water that's been, filling the other parts. That all combined equals the volume of the cone. So that is how we're going to proceed with this question. Now, they are very helpful by giving us some formulas. The first volume is 4/3 pi r cubed plus 4/3 pi small r cubed, and then just 2016 pi. And then the volume of a cone is 1/3 pi radius of the cone squared times the height. Okay, the first thing we can do is eliminate all the pi's, so all these pi's can go. And then we can multiply through by 3. Multiply through by 3, and that will get rid of the fractions. So when you do all that, you will get 4r cubed plus 4 small r cubed plus 6048. Remember, I'm multiplying through by 3. And this gives me just RC squared H. Okay, great. Now all I have to do is substitute everything in. So when I do that, this big R, remember, was twice small r. And then this is just 4r cubed. This is 6048. Now RC, in a very helpful way, I got it in terms of small r. So that's going to be 4 over root 2r all squared. And then H, again, I got in terms of small r, so that's going to be 8r. All right, I only have one variable. I can solve this. So 2 to the power of 3 is 8. 8 times 4 is 32. So that's 32r cubed plus 4r cubed plus 6048. This is going to be, let's see here, 4 times 4 is 16 over root 2 squared is 2. So 16 over 2 is going to be 8. So 8 r squared, and then times 8r. Okay, so this is 36r cubed plus 6048, and this is 64r cubed. Bring the 36 over. 64 minus 36 is 28r cubed over, and that's equal to 6048. 6048 divided by 28 is 216. And then if you take the cube root, you get r is equal to 6. And there you go. That's the radius of the small circle, and that is what they wanted us to figure out. What is the radius of the smaller sphere, I should say, not circle? So number 24, the answer is B.